morning. So today I'm going to go through reviews 7 and 9. So at this point, Miss Stedman, if you could press pause so they can do the homework check. They should be checking review number 6. We will go through the notes for review 7 and review 9, and then if you have time left over, you can review questions from number 6. If you need to press pause, please do so now. So starting off, we're going to go through how to identify maximums and minimums. So remember that if I ask you to find the max of any function, you write, just so that we remember what function to take the max or min of, we always write the word max or min next to whatever the function is. Because the key is, when you're identifying maximums and minimums, you want to take the derivative of whatever the function that they're speaking of. So an example of this would be if I ask you to find the minimum velocity. That's the name of the function. If I wanted to do so, I would have to take the derivative of velocity, set it equal to 0, undefined, and do the sign chart. So that's what I mean by writing the function. So the steps are really, the first thing I want you to check for, are there endpoints? Because if there are, you're going to have to check them. Number 2, think about the domain, especially if it's a ln or log problem. You want to make sure that your sign chart only has to do with the domain. Number 3, you're going to find the derivative of the function. Set equal to 0, undefined, and then you're going to do a sign chart for the derivative of the function. I'm writing it this way purposely because I don't want you to think you're supposed to always find f prime. If they want us to find the maximum of f prime, then we would need f double prime. Alright, and then remembering that if we want to look at, let's do endpoints, interior, max, and min. So I'm just going to do a quick little table. So a maximum at an endpoint, if it's a left endpoint, a maximum will look like this. If it's a maximum at the right endpoint, it'll increase to the maximum. And in the interior, your derivative will be 0 or undefined. It won't be crossed out. Remember, we cross out values that aren't in the domain. And then the signs would have to change from positive to negative. Minimums occur at the left endpoint if we increase, and then right endpoint if we decrease, and then interior, 0 or undefined, not crossed out, and then negative to positive. And the sign charts we're making, remember, will be the derivative of the function that we're trying to minimize or maximize. Another thing to remember for a free response question, sign charts are not accepted as reasoning. So what that means is you will make a sign chart for yourself so that you understand if you have maximums or minimums, but then you'll have to restate it in words or as a sentence. Increasing, decreasing. So remember that a function increases when its derivative is greater than 0. A function decreases if its derivative is less than 0. So an example would be if I ask you, when does acceleration decrease? In that case, I would have to identify the derivative of acceleration and find where it's less than 0, which essentially means I would have to do a sign chart for f prime, which in this case would be a prime of t. And extreme value theorem. So extreme value theorem just kind of goes back to the first screen where we're looking for maximums and minimums. So I'm just going to restate most of you that do not get your max and min problems right, your major reason is because you're ignoring your endpoints. All right, so going back through EVT, if f of x is closed on a to b and continuous on a to b, then f of x is guaranteed a max, I should say an absolute max and absolute min. And remember, our steps for finding absolute max and mins are really no different. First thing you want to double check, are there endpoints? Because if so, they're probably your max or mins. Number 2, domain. Number 3, so I'm just going to call it, just to make it a little shorter at this time, I'm going to say f prime of x sign chart. And number 4, check y values of possible extrema to find absolutes. All right. And creating your sign charts, just remember, if I want to make a sign chart for f of x, the steps are find f of x equal to 0, equal to undefined. Remember in this step that you should factor completely. And you should also have common denominators. When you create your sign chart, double check your domain and endpoints, just to make sure. And then 3, identify a value in each interval. Things that we should remember: the square root of anything is always positive or 0. E to the anything is always positive. Ln of anything, this has to be greater than 0. And actually, let's just call that square root or an even root. And then a few others that I'll squeeze in right here. Absolute value is always positive or 0. And even, anything to an even power is positive or 0. So those are all special functions that you should keep in mind when you do your sign charts. Mean value theorem. MVT, first of all, your function has to be closed. That's our way of saying it's closed by saying a to b, and then continuous on a to b, so the endpoints have to be closed, but differentiable on the open interval from a to b. If they were to say that the function is differentiable on a to b, then that means all 3 requirements were satisfied, and that means MVT is satisfied. What does MVT satisfy? It states that f prime of c is equal to f of b minus f of a all over b minus a. Analytically, you would find your, and you can tell by this little equation right here, first, find f prime of x. Number 2, find the slope between endpoints. And then 3, set equal and solve for x. Mean value theorem, what it does, it guarantees one slope value, and the only slope value that it guarantees is the slope between the endpoints. Okay? MVT graphically. So given that I create a function, doesn't matter what it looks like, things I want to make sure. I want to make sure that from A to B, the function is closed, continuous, and differentiable. So I should not have a cusp, a corner, a vertical tangent, and I also shouldn't have any discontinuities. And what this states is if I were to connect the endpoints, oopsie, a little bit off, and I find the slope between those endpoints, I'm guaranteed that there is at least one place on the function where the slope of the tangent will be the same as the slope of that blue line. So here's one that would be around the same. I would have another one probably here, and then I have a last one here. And remember, you're guaranteed one place. In this case, 3 of them occurred. So graphically, it states that the secant slope, which was in blue, is equal to the tangent slope. In this case, it happened 3 times. You're guaranteed 1. And the other way that we say that the secant line is parallel to the tangent line. Alright, so I think that's everything for review 7. I was going to have you guys do a few questions, but let me get through the notes for review 9 first, and then if there's time left over, I'll do the 3 examples that are here, or at least set you up to make sure that you do them correctly. Alright, review 9. So I'm just going to review optimization. So optimization is, in context, the same exact thing as identifying a max or a min. In context is a little bit harder, so remember the first thing I want you to do, identify the question. Meaning, read the whole prompt. There's going to be a lot of stuff to read, but in the end, it's going to ask you to find some type of max or some type of min. Okay? Number 2, identify if there are endpoints. And in context, usually there aren't endpoints because a lot of times 0 can't be used. So usually no endpoints. If 0 can't be used, then usually there aren't endpoints. But I still always double check for them. And then the steps after that are pretty much the same. Whatever you're trying to identify, if you're identifying the max or the min, you want to find the name of the function, because you're going to need to take the function's derivative. But here is where the function must be in terms of one variable. If not, use extra information to create another equation and then substitute into the function. And the function I'm speaking of is this function here. Alright, so once your function is in terms of one variable, this is where all the steps become pretty much the same. Once it's in terms of one variable, then, that says then, I swear, take the derivative of your function, set equal to 0, undefined. Undefined's nice because in this case, in context, usually you don't have to worry about undefined. And then number 5, just 'cause I'm going to try to squeeze everything on this page here. Number 5, sign chart. And then number 6, answer the actual question. Okay? So, things to remember, the nearest point would be us minimizing the distance formula, which is the square root of x2, minus x1 squared plus y2 minus y1 squared. And remember, what we're going to do is always make sure that x2 is x, y2 is y. This is the x of the point that you're trying to get closest to. And this is the y of point. And in this case, and this is pretty much the only time that you can do this, we actually can ignore the square root. The other way that I talk about this, and I say that when you find your d prime, set it only equal to 0. You don't have to worry about your undefined. It makes this problem a lot easier, and if I have time, I'll show an example of that. Furthest from the origin, furthest means you're trying to maximize distance, which is equal to the square root of x squared minus x1 squared plus y2 minus y1 squared. And if we're talking about the origin, it's kind of nice because the origin would be 0, 0. So you actually end up with x squared plus y squared. This is two variables, so because of two variables, I would have to use extra information to create another equation and substitute in for that y. Alright, so here's an example of an optimization question I do want to go through. So the volume of a cylindrical can with a top and a bottom is 16 pi cubic inches if a minimum amount of tin can be used. So if I'm trying to make the tin can, then I'm trying to minimize the surface area, we'll just call it area. This is what the can looks like with a top and a bottom. So the top of the can is pi r squared. The bottom of the can is pi r squared. And then this is circumference of the circle times height, which is equal to 2 pi r h. So your area formula becomes 2 pi r squared plus 2 pi r h. There are two variables, right, r and h, so there must be other information. I'm going to go back into the prompt. I'm going to read what else it says, and you'll usually find a value. So that 16 pi is the volume. So this is my extra information over here. The volume of a cylinder is pi r squared h, and in this case the volume was 16 pi equals pi r squared h. I'm going to divide both sides by pi, and I'm actually going to solve for h so that I don't have to worry about the square root. So now that I have one variable solved for, I'm going to substitute in, and I end up with that the area is equal to 2 pi r squared plus 2 pi r, and then the h is 16 over r squared. Let's rewrite this guy, 2 pi r squared plus 32 pi r to the negative 1 power. And I'm not going to try and get a common denominator here. What I'm going to do is find the derivative first, which would be 4 pi r. And the derivative, just so you are clear, is with respect to r, which is why there's no differentials. So minus 32 pi r to the negative 2. And this is where I would write the derivative like this, and I would have to get a common denominator. So this would be 4 pi r cubed minus 32 pi all over r squared equals 0. I am going to erase part of this line and use the space over here. So I'm going to set my a prime equal to 0, which would mean the numerator, that's this guy. I'm going to factor out of 4 pi, which would leave me with r cubed minus 8 equals 0. Divide both sides by 4 pi, r ends up equaling 2. This part should make sense. Setting your denominator equal to 0 would make it undefined. R equals 0 would be undefined. That just means that we can't use R to be 0 for a cylinder. It wouldn't make sense. So the sign chart that I'm going to double check would be from 0 to 2 here. 2 is 0. The sign chart, I would notice that the denominator is always going to be positive, right? So I'm only going to have to worry about the numerator, and I'm going to rewrite this in the factored form. Cubed minus 8. And I could actually factor that a little bit more. This piece is a difference of cubes, but I'm not going to worry about that because I can substitute in 1. This would be negative, and then I could substitute in 3, which would make it positive, so I'm guaranteed that this is a minimum. I don't worry about 0 because I can't use 0, and I can't use any negative values over here. This was the A prime's sign chart, and then the last step is answer the actual question. So the question was the height. In this case, I found the radius, and I'm going to go back up here and find the height, which would be 16 divided by r squared, which is 4. So the height is 4. And you want to be really careful about that because sometimes they'll ask you to find the actual volume, or they'll ask you for the radius, or they'll ask you for the height. And each of those questions are related, but have different answers. Okay? This is another example. One thing I mentioned about these weird ones where there's no equation for the function. So it asks you to find the minimum value of the product. So minimum of the product. And that looks really funny, so always name your function. So in this case, I'm going to call the product P. We have 2 variables, so there must be extra information. So I'm not going to finish this one for you. That's your extra information. So x times 2x minus 8, which because we're going to find a derivative, I would actually multiply it out so I don't have to do a product rule. Find your derivative, 4x minus 8, set equal to 0. This can't equal undefined, so you actually end up with x equal to 2. But be really careful. 2 is one of the answer choices, but it's actually not the answer because of what they ask. They want to know the value of the product. So the product is equal to 2x squared minus 8x, or the product is equal to x times y, and you'd use that guy to find y. So in this case, I get 4 times 2 is 8, minus 8 times 2, so the answer is actually negative 8. So be careful with the question. Alright, so there is Review 9 notes. Going back to Review 7, there are 3 questions that I thought we could try. So it's questions number 4, 5, and 7. So I just want to speak about each of them, just making sure that you understand the 3 questions. So looking at number 4, it says that mean value theorem guarantees the existence of a special point on the graph between. So if you notice, this is the function, these are your endpoints. So what are they asking you? They're asking you to find when is the derivative equal to f of 4 minus f of 0 all over 4 minus 0. Okay? In this case, the derivative would be 1/2 x to the negative 1/2, which I would rewrite as 1 over 2 square root of x, is equal to f of 4, which is 2. F of 0 is 0 over 4 minus 0, and we end up with 1/2. I'd probably just cross multiply. Oopsie. I have no idea what I just did. There we go. Please make sure that you go through and complete the problem. The derivative attains its max at, so I want to find the maximum of the derivative, which means to solve this, I would need the derivative of the derivative, set equal to 0, undefined. And that's pretty much how many people get this problem wrong, because if you don't follow my steps of identify who is the function that they're asking you to optimize or maximize or minimize, you'll end up taking the derivative of the wrong function. So in this case, you would need f prime, which would be 4/3 x to the third minus x to the fourth, and therefore in this step you would take the derivative one more time, 4x squared minus 4x cubed, set that equal to 0, undefined, and the sign chart that you would be doing would be for f double prime. And there's no domain issue, so you would have to do the derivatives, the second derivatives sign chart across a domain of all real numbers. And then number 7, same thing. So going through things that I always do now, endpoints, there must be a reason they're giving them to us. Then the absolute maximum of the function, so absolute max. So not only are they asking us to find the max, they want the absolute of the function. So f is the name of the function. That means I'm going to need f prime, which would be x squared minus 8x plus 12, set equal to 0. It's a polynomial, so I don't have to worry about the first derivative equal to undefined. This is factorable. X minus 6, x minus 2 equals 0, so x is equal to 2 and 6. I'm going to do the sign chart for f prime over the interval, oopsie, forgot there's endpoints, of 0 to 9, so 2, 6. This is a parabola facing upwards, so that would look like this with my 2 zeros. So my sign chart would be plus, minus, plus. Therefore, my maximums occur at 0. And if you're still not good with this, just draw the function. So you go up, you flatten, you go down, you flatten, you go up. So that's a maximum, and this is a maximum. So a max happens at 2, and a max happens at 9. So we're going to compare the y values of f of 2, f of 9, and therefore whichever one is larger, that will get us the absolute maximum. Okay, that's it. Alrighty.